All right. Now we are going to solve a problem based on the regeneration of a Brayton cycle, right? So this problem is based on the regeneration unit on a Brayton cycle, and it's asking us to determine that air temperature of the turbine exit, right? Turbine exit temperature, and then it is also asking us what is the net work output of this cycle, and then the thermal efficiency of this cycle, right? So we derived the expression, or we derived the efficiency equation for the regenerated Brayton cycle. So let me make sure one thing about this problem. This problem is asking us a Brayton cycle, so this is not an ideal. So some of the problem will ask you that, will tell you that an Brayton cycle, an ideal Brayton cycle. However, this problem is only a Brayton cycle. This means that it's an actual cycle, right? So first thing, this is very important, this is not an ideal Brayton cycle. It is only Brayton cycle. Only Brayton cycle. This is not ideal. Okay. So that's the most important thing. So some of the problem you will see that an ideal Brayton cycle. Some of the problem you will see that a Brayton cycle, right? So let's go ahead and start with the assumption. So it's saying that it has the regeneration unit, and it is using the air as a working fluid. So assumption will be assumptions, right? So the first assumption, it's a air standard cycle, air standard assumption, right? And then the minimum and maximum temperature of the cycle are this, and the 310 and 1150 Kelvin, assuming that isentropic efficiency of the compressor. So the compressor is running isentropically, right? B, compressor is in isentropic condition, and C, uh, so the turbine efficiency has 65%, turbine efficiency is 82%, and the effectiveness is, regeneration unit effectiveness is 65%. So basically we have to determine these three. And another important assumption about this one, I would like to mention that no delta Ke and delta Pe is negligible. Okay. So now for this problem, what are the known? Okay. So the first thing it's asking that, actually let me draw the diagram first, so then it will be relatively easier to understand what are the known and what are the unknowns. Okay. So this is the TS diagram of regenerated Brayton cycle, right? So this is actual cycle. However, let me draw the first ideal cycle. Ideal cycle, the compression would be a isentropic compression, right? So it will be 1 to 2s. However, in actual cycle, it's something like this. So 1 to 2, and then it will go this. So this is 2, right? And then this is 3, and 3 to 4 should be isentropic. However, in actual cases, this is not isentropic, right? So this is 4, and then it will be like this. Okay. And this is 4s, and then since we have regeneration unit, so it will be 5, and then exit of the regenerator will be 6. So we have pretty much all of those points, right? So basically this is asking us that known is that maximum temperature of this cycle, this one, which is 1150 Kelvin, and minimum temperature of this cycle, which is this point T1, and this is 310 Kelvin, right? So these are the known. So now we have to determine some thermodynamic properties based on these two temperature, right? So let me write those properties. So first of all, at at temperature T1 equals to 310 Kelvin, right? So what are the properties we are looking for, or we need in this one? So we need the relative pressure, we need the enthalpy. So based on this temperature, I will go to table A17. So let me show you what are the things I'm looking for. So if we go to the table A17 appendix, and then basically all the way to the table A17, here is the table A17, right? So in this table A17, excuse me, in the table A17, based on the 310 Kelvin, excuse me, I was trying to, anyway, so we can see right here, based on this 310 10 Kelvin temperature, the properties of the air, we can see that relative pressure is right here. Relative pressure is this one, and then the enthalpy is this one. So we need to record all of this information about the state 1, right, or the temperature 1. So let me, I already grab all those information. So I basically need that at 310 Kelvin I need the enthalpy, right, which is H1, and it will be 310.24 kilojoule per kg. And then I have relative pressure at R1 at T1, which is 1.5546. Now for the isentropic process, let's consider this ideal case, right? 1 to 2s. So 1 to 2 isentropic process in compressor, we can write this formula: PR2 divided by PR1 equals to P2 divided by P1, right? So we know the pressure, and then we know that the PR1, right? Now we need to determine that PR2. So from this expression, PR2 equals to PR1 times P2 divided by P1. Also in this theory class, we talked about the pressure ratio P2 divided by P1, which is the pressure after the compression and pressure before the compression. So the pressure ratio for this problem was, so the PR1 we got 1.5546 times the pressure ratio, it's given here, right here, 7, right? So 1 by, excuse me, pressure ratio is 7. So and then we'll get the relative pressure at 2, which is equals to 10.88. Now based on this relative pressure 10.88, we have to find out the what is the H2s, right, the enthalpy at this point. Okay, now let's go back to the table again, A17. So now we have the relative pressure 10.88, right? So I'm looking at this line. So excuse me, the 10.88, it's in between this number and this number, right? So if I do the interpolation in between these two, then I can determine the temperature and also the um, enthalpy, right? So enthalpy in between, in enthalpy will also be in between these two line. So now we have I already recorded all of those, so which is for based on this relative pressure, the enthalpy H2S equals to um, 400 sorry 541.26 kilojoule per kg, right? And then we have the H2S, H1, everything. Now for from the chapter 7, if you remember, the isentropic efficiency of compressor is equals to H2S minus H1 divided by H2 minus H1. So basically from this equation you can write so we have H1 here 310.24 plus H2H, we just got it 541.26 minus 310.24 divided by eta C. The compressor efficiency was 75% right here. So if I solve this, then H2 will become 26 joule per kg. So we have the H2 now, right? So let's get the properties for, you know, H3 or properties for state 3, right? So for isentropic process 3 to 4, actually for at point 3 here, at point 3 we have the temperature given 1150 Kelvin. Based on that temperature, let's record the enthalpy and the relative pressure, right? So based on T3 equals to 1150 Kelvin from table A17. So we have all this information, right? So now again for process 3 to 4 is isentropic too, right? Here if we look at the process 3 to 4s, this is the isentropic process. So for this isentropic process, we know the relationship as well. So PR4 divided by PR3 equals to P4 divided by P3. And then we know that PR3, it's basically 200.15 times. So P4 divided by P3 is also the pressure ratio, right? So the pressure ratio is 7. However, this P3, it should be P3 over P4, but if we do the P4 over P3, it will be 1 over 7, right? So PR4 equals to so based on this PR4, let's go back to the table A17 again, and from that table A17 we have this information, right? Based on this pressure ratio H4S, which is equals to if we do the interpolation, it will be 700, excuse me. Now we know the definition of isentropic efficiency of the turbine, right? Isentropic, which is H3 minus H4 divided by H3 minus H4S, right? So we have all of those information. We can write H4 H3 minus eta turbine of H3 minus H4S. So the efficiency of the turbine here it's 82%. So 0.82 times H3, we got 9.25 minus H4, we got 7. So if we solve this, it will be 803.14 kilojoule per kg. So based on this H4, now we have to determine that from the table A17 we'll get the T4. If we do the interpolation, we will get the temperature T4, which is 782.3 Kelvin. So this is the answer, right? Basically this is the turbine exit. Temperature. Then B is asking us to determine the net work output of this system, so which is, we know all of this information now. So W net equals to W turbine minus W compressor, right? So the turbine work is H3 minus H4 minus compressor work is H2 minus H1. So basically if we plug in all this information, 1200 19.25 minus 803.14 minus H2 is 618.26 minus 310.24. So if we solve this, we'll get net work output equals to 108.09. So it's a positive quantity, and this much of amount of work is generated or produced by this regenerated Brayton cycle. So now we are going to take a look on the part C, right? Or we're going to solve the part C, which is the effectiveness. Basically the effectiveness of this system of our generation equals to regeneration equals to, we know that H5 minus H2 divided by H4 minus H2. We don't know the H5, right? So basically H5 will be H2 plus epsilon H4 minus H2. So we know the effectiveness of this system and also all those thermodynamic property. 618.26 plus effectiveness of this turbine of this regeneratory unit was 0.65 times so H5, if we solve this, it will become 738.43 kilojoule per kg, right? So now we know that we can determine the Q in, right, of this system. Basically the Q in is happening here, right? So this is the Q in. So this Q in will become H3 minus H5, right? So excuse me, so this is for regeneration unit, Q in regen. However, this is the actual Q in, right? Okay, so it will be 1219.25 minus 738.43. So the Q in equals to 480.82 kilojoule per kg. So we have the Qn and W net of this system, which is 108.09, right? Excuse me, this is kilojoule per kg. So the efficiency of this system, or thermal efficiency of the Brayton cycle, will be 1 minus excuse me, since we have both of them, I can write this formula, W net divided by Q in. So W net we got 108.9, 480.82. So at a thermal (22.5%).